Hello everyone, and welcome to this first video on the series on IGCSE mathematics. I am Sohaib Khalid, and I will be taking you through the IGCSE mathematics syllabus over the course of the next few months. Without going into too much detail about how this series is going to be put together, because that sometimes gets too laborious to hear, let's just dive right into the mathematics. So the very first concept that we have to wrestle with in IGCSE mathematics, in my view, is ratios. We have to make sense out of what are ratios. We're going to start with a very basic notion. We're going to start with the idea of a size of a number. So we're going to start with size first of all. We're going to see that we are all familiar with the natural numbers. The natural numbers are just the numbers 1, 2, 3, and so on and on and on. They go on and on beyond our sight. These numbers have a certain size associated with them. Just like in the real world, things that we come across in our daily lives have different quantities associated with them. For example, a wooden block or a wooden log may have a certain weight, a certain mass. It may have certain density. All these quantities are of no use to us if we cannot compare them with other quantities. So suppose we have a log here, a wooden log. So this is wood. And we have a smaller log, and we want to compare their masses together. Well, we can immediately see that if they are made of the same wood and this one is smaller, we can already see that this one is going to have a smaller mass than this one. Similarly, within the natural numbers, when we are given any two natural numbers, suppose we are given the natural numbers 783 and 219, it is always possible for us in the real world to actually compare any two natural numbers. In other words, what I mean to say is, it is always possible for us to decide whether one number is larger than the other, or the two numbers are exactly equal to one another. So this is a very important property of natural numbers and of the real world, that given any two quantities, we can actually compare the two quantities. In other words, for these two numbers, the relationship between them is that 783 is larger in size than 219. So this fact is known as the Trichotomy Law. I don't want you to remember the name, but I want you to get the idea. We want to actually understand that given two natural numbers, we can always decide whether one is equal to the other, or the one is larger than the other, or the other is larger than the one. So having that notion in mind, let us now look at a scenario given to us. We are presented with the following problem. We are presented with a problem of comparing the mass of a cricket ball. So let me draw in the cricket ball. Let's draw in pink. They're using pink cricket balls now. So suppose you want to compare let me just color it in. So you want to compare the mass of a cricket ball with that of a tennis ball. I conveniently have yellow color to represent tennis balls. So you want to compare the mass of these two balls together. We know from our everyday life that the cricket ball is heavier. It is more massive than the tennis ball. But that is not enough. That does not provide us with as much information as we'd like. So what we could do, if we are presented with the problem of comparing their masses, is we could take a pan balance, I believe it is called a pan balance, and we could start placing in the pan balance these two objects. So for example, I would place in one side a cricket ball. Alright, I place in a cricket ball, and what I find out is that the balance will tip towards this side. It's going to tip in the direction, or on the side where the cricket ball is placed, because the cricket ball is heavier than nothing. There is nothing on the other side. So what we do then is, well, we say, okay, so we put in a tennis ball, and we see that the balance might go up a little, but it won't balance. This side would still be lower than this side. We keep putting in tennis balls, and at some point we're going to find out that the weight of these 3 tennis balls, for example, is greater, or the mass of the 3 tennis balls, pardon me, is greater than the mass of the cricket ball. So what that is going to do is that's going to tip the balance in the favor of the tennis balls. So we could do the following. We could say, okay, 3 tennis balls are heavier than 1 cricket ball. So what about 2 cricket balls? We add 2 cricket balls now. If we do that, then perhaps the balance might tip in the favor of the cricket balls once more. So we could keep doing that. We could keep doing this process until we reach equilibrium, until we balance the scale. Once we do that, suppose we have balanced the scale when there were 2 cricket balls on this side and 5 tennis balls on this side. Suppose this is the situation when the balance was reached. That 2 cricket balls had the same mass as 5 tennis balls. Now this suggests to us a relationship between the masses of the 2 objects. The mass of the cricket ball and the mass of the tennis ball occur in a simple ratio, a ratio of 2 numbers. So what we say is then that the ratio of these 2 masses is the same as the ratio between the ratio of the cricket. So this is important, the order is important. The ratio of the masses of the cricket ball and the tennis ball occur in the following ratio. There are 5 tennis balls, so 5:2. The ratio of the mass of the cricket ball to that of the tennis ball is the same as the ratio of 5:2. In other words, there is this idea that the relative size or the comparative size of 5, when we compare the size of 5 with the size of 2 in the natural numbers, it is in a way the same as comparing the weight or the mass of 1 cricket ball and 1 tennis ball. In other words, if you took 5 of these tennis balls and 2 of these cricket balls, the 2 weights would be exactly the same, or the mass if you'd like. So that is one very good visualization of comparisons and ratio. But there are others. There are others which are as important, if not more. So let us look at another way in which we can view what a ratio is. Suppose we have a length. Suppose we have a length and we call it A. We can do that. We can give the length a name, and that name is A. We often do that in mathematics, by the way. And we have another length B, right? B. Now, what we could do the same thing. We could take A and put together a bunch of A's together, A, and another A, and we could put together a bunch of B's, and when the 2 lengths became equal, we would be able to tell the ratio between A and B, just like we were able to do with the cricket ball and the tennis ball. We were able to put them in the 2 different sides of a pan balance and when the two sides became equal, we realized that that was the ratio in which the two quantities occurred. In the same way, suppose you have a ratio, and that ratio is 5:4. So let's just forget everything and look at this ratio now in terms of numbers. And suppose a carpenter now comes to you and says, well, I need to cut wood I need to cut pieces of wood which are in this ratio, whose lengths are in this ratio. So what would you do? Well, you would take a length and divide it into 5 equal pieces, 1, 2, 3, 4, and 5. And then, because all these pieces are equal, you would tag along now 4 pieces which were each equal to these. Alright, so let me label this now. So this is your pink. So this was the 5 equal pieces in which you divided the first length of the wood, and then you took another length and you put together with this length 4 pieces, each of which were equal to each of these pieces. So here's a piece, 1, 2, 3, 4, that's it. So this length, the yellow length now, the yellow length and the pink length are in the ratio 5:4. So if we had called this length A and this length B, then this would be A and this would be B. So the carpenter would have said, okay, I need to cut the wood in 2 pieces whose lengths are in the ratio 5:4, and you would have done this to give him that length. Now all that is easy, but suppose there is a point of confusion here. Suppose we had not cut A into 5 equal parts, we might have decided to cut A into 10 equal parts, like I'm doing right now. And we could have added 8 more equal pieces, right? We could have added 8 more equal pieces. Then A would have spanned not 5 but 10 equal pieces, while B would have spanned 8 equal pieces. So clearly 5:4 is the same in disguise as 10:8, because clearly the ratio of this length A to this length B is the same as this, right? Because we didn't do anything with the lengths, we just divided our pieces into more equal pieces. So 10:8. So what does this suggest? This suggests then that a ratio 5:4 is really the same as the ratio 10:8. In other words, you can multiply both sides of a ratio, both parts of a ratio, by the same number and get an equivalent ratio. That is a very important concept that is going to help us solve problems regarding ratios. So in the next video we will do a few examples in which we'll try to understand how to actually start solving problems that involve ratios. So I'll see you then. I hope you'll join me for that. Thank you for listening.